All right. Hi guys, this is another video about the total energy of a heating curve problem. So this is from your heating curve worksheet where all the specific heat of ice, water, molar heat of fusion, molar heat of vaporization is going to be recorded. So all that information you're going to need for problems 1 and 2. I'm actually going to do the most extensive problem number 3 for you. It's about an ice sculpture of the Olympic rings commissioned for the upcoming Winter Olympics, when the finished sculpture will have a mass of 19.6 kilograms. We want to know how much energy in kilojoules it would take to completely vaporize the sculpture if the sculpture started at -10 degrees Celsius. So like we have before, let's sketch out this temperatures. This is where we're starting. We want to completely vaporize the sculpture. Vaporization of water happens at 100 degrees Celsius. The other important temperature we need to keep track of is where water melts. The ice turns into liquid water. So I'm going to have 4 parts to my graph here. Q equals MC delta T. I'm going to have a section for heat of vaporization. I'm going to have another Q equals MC delta T. And since I want to completely vaporize that ice, turn it into gas, I'm going to have a final 4th section. So I'm going to have a first section, a second section, a third section, and a 4th section where you will see the solid. You will see the solid melt into the liquid. You will see just the liquid, and then you will see the vaporization of that liquid ice sculpture into the gaseous state. We're not heating up the gas in that section, but that's how I'm going to map this out. And again, we'll need to use different specific heats of ice, specific heats of water, and molar heat of fusion, and molar heats of vaporization. This is a big problem. All right, let's start with section 1. So to outline section 1, we're going to have the Q of our solid ice is all right at this time. So we'll need our mass of our ice, specific heat of our ice, delta T of our ice cube. I guess it's not an ice cube, it's an ice sculpture. And it masses at 19.6 kilograms. I want to use joules, I want to use grams here. So just like joules, there's 1,000 grams in 1 kilogram, or kilo stands for 1,000. So I'm going to move my decimal place 3 places over to the left. So I'm going to end up with 19,600 grams here. And my specific heat of ice on the previous page is 2.1 joules per gram degree Celsius. And my change in temperature is T final 0 degrees minus T initial -10 degrees. So my change in temperature is 10 degrees Celsius for this section. When I multiply that through, I end up with 411,600 joules, or move my decimal place over 3 places to the left, 411.6 kilojoules. All right, on to section 2. I'm going to need to use the delta H of fusion for this section, which is given on the previous page. But before I can start using the delta H of fusion, I'm going to have to take my grams of water to moles of water. So I know I have 19,600 grams of water. It's going to be a lot of moles, X moles, because there's only 18 grams of water and 1 mole of water. So we are going to end up with 8.88 moles of water. We've never had that many moles. That's a lot of moles. Let's find out how much energy there is now. So if I have 1,888.88 moles of water, I want to know how much energy that is. The delta H of fusion on the previous page tells me it takes 6.01 kilojoules of energy to raise 1 mole of water from solid to liquid. So I can write that in here. 1 mole takes 6.01 kilojoules of energy. I cross multiply, and I end up with 6,544.2 kilojoules. Don't need to convert that. It's already in kilojoules. So that's my next part. This is a big ice sculpture. A lot of energy is required to melt this. All right, let's do section 3. This one is going to be Q of our liquid water, mass of our liquid water, specific heat of our liquid water, delta T. I already know my mass in grams. I know my specific heat. This one I know off the top of my head. And my delta T, 100 minus 0 gives me a delta T of 100. 100 degrees Celsius. Multiply this through, another really big number here, folks. This is going to equal, the energy of the liquid is going to be 8192800 joules, or 8,192.8 kilojoules. I'm going to round all my sig figs at the end. Almost there. We're on to section 4. We're going to have to use the delta H of vaporization because I want to vaporize all 19.6 kilograms or 19,600 grams of water. So delta H of vaporization on the previous side takes a lot of energy to vaporize. It's going to be a big number. I already know my moles of water. I don't need to do this step again. So I'm going to take my 1088.88 moles of water. I know how much energy it takes to vaporize. If I had 1 mole of water, it would require 40.7 kilojoules of energy. I'm going to multiply through, and I end up with a big number, 44,318.23 kilojoules of energy. That's a lot of energy. All right, take a second, see if you can total up all of this data, add them up for your total energy, see if you get the same thing.
Attention, we have 1 bus change, bus 10.
All right, it's the end of the school day here when I'm recording. So I paused for a second, and while the announcement for the buses were going on, I added up all the parts of my kilojoules of energy. My calculator told me that there is, oh my goodness, 59,466.83 kilojoules of energy needed. With sig figs, your total final answer is going to be 59,500 kilojoules, because I know my initial temperatures were given with 3 sig figs. That's why I rounded to 3 sig figs with my final answer. This is a big problem. The only bigger that this problem can be is if I heated up that water and superheated that steam to a higher temperature, then I would have a 5th section to add. But since I'm only trying to vaporize, I'm not superheating the steam, I'm going to stop there. So this problem is 4 out of the 5 possible sections you can have on a heating curve problem.